We'll get started. Our first speaker today is Ashika Capirala. Ashika is a fourth-year PhD candidate and NASA Finest Fellow at Purdue University. She completed her BS in Earth and Space Sciences from the University of Washington and now applies her geochemistry background to questions of habitability and evolution on early Earth and Earth-like exoplanets. Her research uses 3D Earth system models to study how ocean landscapes can vary across space and time and constrain the range of habitable environments and potential biosignatures on exo-Earths. Their talk is entitled Using Ocean Dynamics to Map Marine Habitability on Earth-like Exoplanets. Ashika, whenever you're ready, take it away.
Thank you so much for the intro, Tiffany. Just getting my screen set up. Okay, hi everyone, my name is Ashika, and as I mentioned, I am a fourth-year PhD candidate at Purdue University in the Purdue Habitability and Biosignatures Lab with Dr. Stephanie Olson. Today I'm really excited to talk to y'all about my research using ocean dynamics to map marine habitability on Earth-like exoplanets. Can I just double check that you can see my screen because I don't have a...
Yes.
Okay, awesome. Yeah.
Looks great.
Sorry, it's so weird today. Okay, so just to get started real quick. So in our search for habitable terrestrial exoplanets, our search motto is usually to follow the water and look for planets that might have the right conditions to host liquid water, because water is the most basic constraint for life as we know it. However, in the search for these habitable planets, we might find planets that are just like Earth, or like any version of our Earth that it has existed over its 4 billion year habitable lifespan. And these exo-Earths, if they have liquid water, they might very well also have oceans like we do. And seeing as we use Earth as a blueprint for what exoplanet life might act or evolve like, we need to consider that life on Earth was confined for most of geological history to our oceans. And if we see a potential exo-Earth, there's a good chance that life is in its ocean as well. And to better understand and contextualize biosignatures and habitability on these planets, we need to better understand how habitability varies through space and time on these exo-Earth oceans. So Earth provides our only data point, but a very important data point for studying Earth-like ocean worlds due to different states it has experienced over time. And so my research looks at what can Earth tell us about the potential for life in exoplanet oceans. Moving forward, I'd like to quickly walk you through the specific definition of life that I'll be discussing today. So Earth's biosphere is complex, and so I'll be talking about complex life. And there are different definitions of what complexity means and its own entire field of study, but within this talk I'll be referring to specifically complex marine life here as at least multicellular. So asking how we got to a complex biosphere on Earth is an important question to ask for exoplanet habitability, because as I'll explain over the next couple of slides, complex life is more likely to alter its planet in a way that is remotely detectable. So on Earth, our biosphere is fueled by the sun and by nutrients in the ocean. And nutrients, I'll be referring to phosphorus throughout this talk. And to form larger marine biospheres with more detectable signals, you need to translate more stellar energy into carbon biomass and oxygen through a reaction like photosynthesis. However, this biomass is not energy until it can be respired. But if you can respire it, you can transfer this energy to higher and higher complexity organisms in your food chain. And this is what forms the foundation of our complex biosphere. The most efficient way that we get this energy transfer through different forms of complexity is aerobic respiration with oxygen, like we do as humans. And this makes oxygen our planet's largest energy reservoir. So in turn, oxygen availability in the ocean becomes a major control on the habitability and survival for these higher level life forms in the marine biosphere. At the same time, you also need to produce biomass, and to produce biomass, you need nutrients. And the distribution and the 3D spatial patterns of all three oxygen, carbon, and nutrients in the ocean is controlled by physical circulation, which has varied a lot through Earth history and will vary a lot on exo-Earths. So co-evolving with circulation is Earth's oxygen history, um, creating another reason that habitability has varied over time. So here's a simplified diagram of the evolution of atmospheric oxygen on Earth. I'm pointing out atmospheric oxygenation because at our modern levels today in the atmosphere is about 21% of our atmosphere is oxygen. And these levels are because of the complex biosphere that we know on Earth today. And it makes the most detectable way that life has altered our planet. This means that oxygen is a strong biosignature candidate for detection with future missions looking for biosignatures on Earth-like exoplanets. Another reason that I'm illustrating atmospheric oxygen is because despite its rise over time, it does not necessarily translate to ocean oxygenation, which is controlled by a set of more complicated processes. And this was the case on Earth, as I'll outline in just a quick walkthrough of our history. So in our past, we started out with not a lot of atmospheric oxygen. Note this is a log scale, so this is 1/100% of modern levels. And within this window is the evolution of photosynthesis, marking a lag between the evolution of photosynthesis and the first appreciable rise of atmospheric oxygen. In this next shaded region here, oxygen was about up to 1% of modern levels with a pretty hefty error bar in this shaded green region. A coinciding event in this window is the evolution of the first multicellular life, quickly followed by the evolution of the first animals when we started reaching modern levels of oxygen in our atmosphere. So importantly, I want to point out that all of these evolutionary events are happening in the ocean, and specifically within the marine biosphere is increasing in complexity. So this is 3.5 billion years of Earth's inhabited lifespan where complexity was evolving just in the ocean, just to underscore the importance of marine habitability. However, in this window over here, after we reach modern atmospheric levels, we reach total ocean oxygenation. So this is interesting. All of this evolution was happening before we considered the ocean to be fully oxygenated. So a couple of questions this brings up that I look at in my research is why was the ocean poorly oxygenated for most of Earth's history? And what factors can influence ocean oxygenation on other worlds? And one of these factors is considering how ocean circulation varies through time and from planet to planet. So here's a schematic of some of the processes controlling oxygen in the ocean, but more spatially oriented, so I can explain how circulation factors into things. So for the purposes of this explanation, we'll assume that we have modern levels of oxygen in this planet's atmosphere. So you have photosynthesis, and this photosynthesis is sustained by the supply of nutrients transported by physical circulation to the surface in a process called upwelling. At the same time, oxygen gas exchange is happening at the surface, where oxygen from your atmosphere can dissolve into the surface ocean, making this layer pretty well oxygenated. This oxygenated surface water then gets transported into the deep ocean through downwelling and deep convection. At the same time, some of this oxygen gets respired and re-releases nutrients into deeper waters, kind of completing the cycle. And you end up with this pump system where biological processes are coupled to physical circulation. And as I've mentioned, the circulation is going to change over time and space. And my research looks at to what extent did it change and what was the impact on life. So two factors that I'm investigating and their impact on circulation. There are multiple factors that could impact circulation, but here I'll be talking about planetary rotation because atmosphere and ocean circulation are directly controlled by the rotation of a planet. And not only has Earth's rotation changed over time, for example, we were spinning up to 4 times as fast when life was starting out on Earth than we do today. But rotation periods will also vary a lot for exo-Earths. So not even entering the world of synchronously rotating planets and just considering a range of rotation periods close to our modern 24-hour day, you'll still get a lot of variation from planet to planet. The second thing I'll talk about today in affecting circulation is continental configuration, because continents also have varied across time and space on Earth, and they are important for determining the barriers and paths to flow in the interconnected world ocean. So I'll quickly overview the methods that I use to investigate this parameter space, and then I'll jump back into discussing planetary rotation. So the model that does most of my heavy lifting is CGNE, and this is a 3D Earth system model with an ocean that does physical circulation as well as biological processes, and it tracks things like the distribution of oxygen and nutrients and so on in the ocean. However, it does not have a circulating atmosphere. And this is a bit of a problem because, as I mentioned, the atmospheric circulation is also impacted by things like rotation rate. So to remedy this, I use a 3D atmospheric model that does atmospheric circulation and resulting climate. And I use this to derive boundary conditions for the ocean model. So I end up with a model setup that is capable of doing ocean circulation, representing biological processes, and also representing changes in the atmospheric circulation that impact the ocean in turn. So going back to rotation and its influence on circulation, sort of high-level overview of the theoretical prediction for this is that rotation is going to modulate the amount of upwelling and downwelling in your ocean via the Coriolis force. So this modulation happens because winds at the ocean surface are driving horizontal transport that this horizontal transport is going to either diverge and create areas in the ocean that are like a vacuum and that draw up deeper waters. This is what's causing upwelling. Or there are going to be areas where this horizontal transport is converging and pumping water downwards, and this is downwelling. So an important relationship is that the strength of the Coriolis force is going to scale this transport and therefore upwelling and downwelling as well. So to simplify it quite a bit, the theoretical prediction is that rotation period is proportional to this volume transport. And so we might expect to see more upwelling on slower rotating planets. And we do see more upwelling on slower rotating planets. So before I walk you through these plots, I just want to point out that about these experiments, that all I'm changing is rotation period. These are modern Earth experiments with like a modern Earth initial climate, modern continental configuration, and so on. The only thing changing is rotation period. So on the left is a plot of upwelling, just summed up on the ocean surface and then normalized to the value at 1 Earth day or 24 hours. And upwelling is increasing pretty dramatically across the surface of the entire ocean, as well as in more localized areas, such as the equatorial region and along coastlines, which is where we expect to see more upwelling theoretically. And on the right plot is carbon export from the surface, which is a quantitative measure of photosynthesis. So photosynthesis or productivity is also increasing significantly globally as well as in these more local regions. And what all of this together implies is that slower rotating exo-Earths, ones that spin more slowly than Earth today, could have larger biospheres than we do and make them super habitable. What this also means is that planets that spin faster than Earth in this tiny region over here, faster rotation could suppress a biosphere and lead to a reduction in photosynthesis, reduction in upwelling, and a less habitable biosphere overall. So this pertains to photosynthesis, but I've also mentioned that upwelling and downwelling control dissolved oxygen in your ocean. So I'll be looking at that next. So as expected for more upwelling, you would also get more downwelling as it's controlled by the same physics. And what I've plotted here is depth profiles of dissolved oxygen in the ocean interior, just averaged across the ocean. And the thing that stands out is going from a faster rotating planet, so this is half an Earth day, to a slower rotating planet, double an Earth day. You increase the amount of dissolved oxygen in your ocean interior, and you also increase your minimum ocean oxygen concentrations. So this is going to bode well for complex life at these intermediate depths that rely on having more dissolved oxygen for their survival. However, on the other hand, on these faster rotating planets, again, you might suppress ocean oxygenation, despite the fact that you have modern day levels of atmospheric oxygen, or as we might say, remotely detectable levels of atmospheric oxygen. So this is all relevant for, again, having modern day levels of atmospheric oxygen, but as you might remember, Earth did not have these levels in its atmosphere throughout most of its history. So going back to this plot, there's this huge region of time where we did not have that much oxygen. So we might expect to find Earth-like planets that have low oxygen in their atmospheres as well. So under a more oxygenated atmosphere, the main source of ocean oxygen is going to be dissolution from the atmosphere, but under a poorly oxygenated atmosphere, the main source of oxygen is going to be photosynthesis, and the majority of your ocean is going to be anoxic. Only the surface is going to have oxygen, and only where photosynthesis is happening. So we might expect totally different dynamics of oxygen in the ocean on poorly oxygenated planets. So running a set of simulations, which are the same in changing planetary rotation period, but this time I hold atmospheric oxygen concentration at 1% of modern levels. We see a counterintuitive result emerging where oxygen in the surface ocean is decreasing really significantly when rotation slows, going from, again, half a Earth day to double an Earth day, with planets rotating more slowly than this one, having qualitatively similar surface oxygen distributions. And this might be a surprising result because I mentioned that slowing rotation increases photosynthesis and therefore should increase oxygen production. And this is still true. The physical component of the circulation pump is still the same as the previous experiments. We're still increasing nutrients and photosynthesis on slower rotators. But there's an interesting physical dynamic happening as an unexpected effect of changing atmospheric circulation at the same time. And this is because as you change atmospheric circulation, areas where you have faster wind speeds are overlapping areas where you have more oxygen in your surface ocean. And these faster wind speeds are mixing up the water and causing a lot of the dissolved oxygen to escape to the atmosphere. So that's what's causing all of the oxygen to leave the ocean in these slower rotator simulations. So this is an interesting result of marine oxygen dynamics that kind of only comes about from doing 3D modeling like this. So on planets like these, where oxygen distributions are quite suppressed, this will likely impact the evolution of animals of complex life in your surface ocean by creating oxygen stress. Basically, they can't breathe. However, at the same time, on planets like this one, because all that oxygen is leaving the ocean to be in the atmosphere, you would increase the likelihood of having more oxygen in your atmosphere, making the planet potentially more detectable. So you decrease your potential for complex life, but you increase your potential for biosignatures. And that's an interesting contrast because despite the fact that you might be more likely to pick up atmospheric oxygen on this planet, it doesn't necessarily mean that it's a good environment for the evolution of complex life. Okay, so at this point, I'm going to pivot a little bit to talking about circulation changes as a result of changing continental configuration. And to do that, I'm going to just quickly orient everyone to how we might expect circulation to change with different continents. So here is a diagram of our modern ocean circulation. Normally, this is referred to as the ocean's conveyor belt system. And it's a result of our modern planetary state. So our modern climate, our continental configuration, the depth of our ocean basins, and so on. So this is very unique to our continents as we know them today. And we might expect that if continents were in different locations, that this conveyor belt circulation would be completely different. Another thing that I want to point out about the circulation is that not only is water being transported horizontally across the surface of the ocean, but also vertically. It's sinking to deeper levels in the ocean, and from deeper water, it's also rising up to the surface. So the important part of this process is the sinking of water deeper into the ocean, and those regions, the regions where that happens, are partly mediated by continents. So for example, we uniquely see that kind of deep convection happening up here and down here. So we might expect, as deep convection varies with different continental configurations, this might impact how oxygen is transported to the interior. So just bringing back this diagram to point out that once you have an oxygenated surface layer, this water that holds oxygen can be transported deep into the ocean and then moved around in the very bottom layers to control how much oxygen is there and where it's available. So these next sets of experiments, I will just be changing continental configuration, keeping everything else constant, climate, orbital parameters, and so on. And I will be investigating a set of randomized continental configuration. This is just a set of 25 of them for illustrative purposes. So assuming everything else about the planet is the same and Earth-like, how much of an impact does changing just continental configuration have on ocean oxygenation? So these are maps of dissolved oxygen at the deepest layer of the ocean in my model. So this is about the bottom kilometer of each planet's ocean. And what is plotted here is dissolved oxygen concentrations in the water. So the first thing that stands out is that some of these are pretty well oxygenated or pretty consistently oxygenated, and some of these are really poorly oxygenated, with almost no or like minimal levels of oxygen in their interior. And this is a bad sign for habitability because this implies that large regions of the interior are deoxygenated, and this can lead to, for example, mass extinction events, like several mass extinctions on Earth that were driven by marine anoxia. So this is not a favorable state for marine habitability and the survival of complex organisms in the ocean interior. However, this one is. And the difference between being well oxygenated and poorly oxygenated ends up coming down to circulation. So also on these maps, I've plotted out how fresh the water is in terms of these contour lines. So by fresh, I mean how recently the water came in from the surface, measured in years. So these higher oxygen concentrations, the lighter colors, correlate pretty well with regions of water that more recently came in from the surface, carrying oxygen from more shallow layers of the ocean. However, the surface oxygen concentration and even the atmospheric oxygen concentration, it does not do a good job of predicting deep ocean concentrations separately from circulation. And to illustrate this, I've just got a scatter plot of all my configurations where each dot represents a different experiment. On the y-axis, I've got deep ocean or benthic oxygen. just showing that there's a very nonlinear relationship between the amount of oxygen at the surface and the subsurface with deep ocean oxygen. And again, this is just pointing out this large amount of scatter is just pointing out that circulation is the main control on deep ocean oxygen and can decouple deep ocean oxygen from detectable atmospheric oxygen. So just quickly summing up in the last 30 seconds or so, ocean circulation across space and time can determine spatial patterns in marine habitability. Talking about rotation and its impact on circulation, slowing planetary rotation can enable more prolific biospheres and increase oxygen for complex life. For early Earth exoplanets with low oxygen in their atmosphere, slower rotation could increase biosignature potential but limit complex habitability. Jumping to continents, circulation has a very nonlinear dependence on continental configuration and ends up being a factor that can decouple interior ocean oxygenation from surface conditions. Quick last few seconds, I just want to thank my funding sources, my advisor Stephanie, and my collaborators Celine and Camilla. And that is all. I'll open to questions. Thank you.
Thanks so much, Ashika. All right, I think we have time maybe for one quick question, either in the chat or using the raise hand tool. Great talk. Yeah, Heis, go ahead.
Hi, this is a great talk, very interesting. I had sort of a general question and then a more specific follow-up. So is most of the Earth's oxygen like in the atmosphere or in the ocean? And does that change if you change like rotation periods and the other factors you looked at?
Yeah, that's a great question. So in these experiments, it would be really interesting to model absolute amounts of oxygen, how much is going into the atmosphere versus the ocean. But just for the sake of fixing a variable, I do keep atmospheric oxygen constant. So I can't model how much is accumulating in terms of like beyond the fluxes going into the atmosphere. It's not changing the atmospheric concentration. So that would be a really interesting thing to investigate, just to look at how it impacts maybe abundances for detectability and so on, though.
Okay, thanks.
Yeah, totally agree. Okay. All right, in the interest of time, let's move on. But thanks so much, Ashika, for a great talk. And if you want to